Hello everyone, and I welcome you to the lecture series on thermodynamics, where today we are going to discuss the remaining concepts which we left in the first lecture for the basic concepts chapter. So today we are going to discuss a specific volume, then pressure, and then temperature. So these are the properties which we are going to use a lot in the subject of thermodynamics. Okay, so let us start with a specific volume. Okay, and to discuss a specific volume, we need to understand the concept of continuum. So what is a continuum? So, and to define it more appropriately, we can say that when substances can be treated as continua, it is possible to speak of their intensive thermodynamic property at a point. So this term at a point is important. Suppose if we are talking about density, which is an intensive property, and if you can recall, intensive, we already defined that it is independent of size or independent of size or mass. So the properties which are independent of size or mass, they are called intensive thermodynamic property. And if that property, we can say that it can be defined at a point by some value, then we can call that medium as continua. Okay, now the definition of density. So to define the specific volume, we will see that how density is important. So to define density, let us define density. So density is equal to, it is a bit more technical when V tends to read as M over V, where M is mass, V is volume, and V dash here defines the smallest volume for which a definite value of this ratio exists. So V dash is the smallest possible volume for which the ratio, which is M over V or density, does not change. Okay, and this is the definition of density, but we have yet not defined what is a specific volume. And to define a specific volume, you can just take the reciprocal of this density. So a specific volume is nothing, and we denote it by V. It is ratio of density, or sorry, reciprocal of density. Reciprocal of density. Now we need to define another property, which is like pressure. And we know from our mechanics class, and we know it from all our physics class, that pressure is nothing but a ratio of force over area, force to area. So pressure is nothing but normal force to area, and there is nothing special about it. We already know it from our physics class. So whenever some force is applied on an area, and if you take the normal component of that force and you divide it with area, you will get the pressure force or the pressure. And the unit is Newton per meter square, which is also making sense because force has units of Newton and then area has units of meter square. Now we also need to understand few of the devices. For example, for pressure measurement, we consider a particular device which is called manometer. What we do is we take a tank. Suppose this is our tank. Oh, sorry. This is our tank. Okay, and then you attach a U-shape tube here. Okay. And U-shape tube here. Which is filled with some liquid. And in this tank you have gas. And if you want to calculate the pressure, and here you know that it is like atmospheric pressure, then the difference between liquid level is like L, and this liquid has density rho. Suppose this gas has some pressure like P, and if you can recall it from your physics class, you know that the pressure at these two levels, which is pointed out by A and B, so pressure at these 2 points should be equal. And then PA is nothing but the pressure of the gas, so P, and PB is nothing but, PB can be broken down into P atmospheric plus rho of the liquid G into L. So this formula can be used to get the pressure of the tank, and this is a kind of device we use for pressure measurement. Now we need to understand what is temperature. What is temperature? Now temperature has certain features. So first, it is intensive property. So it is independent of mass. Whether you are taking a small quantity or a large quantity, the temperature will not vary that much. Then it is very difficult to define the temperature. So definition of temperature is difficult to give. And we can recall from our high school classes that we used to call that degree of hotness or coldness, but that doesn't actually define the temperature, and we will see how we are doing it in thermodynamics. So thermodynamics suggests us like what we saw in lecture 1, something like thermal equilibrium. And thermodynamics uses this concept of thermal equilibrium to define the temperature. So it says that suppose if you have an object A, which is in thermal equilibrium with object C, and then consider another scenario where object B is in thermal equilibrium with object C. So basically what I mean here is temperature of A is equal to temperature of C, and here temperature of B is equal to temperature of C. Then we can say that A and B are also in thermal equilibrium with each other. So these two can be summarized as, okay, body A is also in thermal equilibrium with body B, which means TA is equal to TB. And from here, we can say that the temperature of body A is equal to temperature of body B. And that's how we define temperature in thermodynamics. And this is nothing, but this is also called like Zeroth law of thermodynamics. Zeroth law of thermodynamics. So we have covered one law in this basic concepts chapter. So what is zeroth law of thermodynamics? By definition, we can say when two bodies or objects are in thermal equilibrium with a third body or object, then they are in thermal equilibrium with each other. And from here, thermometers are also designed. So from here, the concept of temperature comes, and then we design thermometers like that. So you can consider thermometer as our object C, okay, where we are considering, okay, if thermometer is in thermal equilibrium with some body, and then we know the measurable property of that thermometer, then we can say that we can find out the temperature of the object. So we have to study this type of thermometers also in this thermodynamics, just to know that how can we arrive at, how are we measuring temperatures. So thermometer also has one definition, kind of. So thermometer is basically object with, or we can say an object with at least one measurable property, at least one measurable property that changes when temperature changes. So all of us have seen that there is a object like this where we fill mercury here, and then once you supply heat, then this can expand, and then we have readings here on the thermometer, and then we can say that, okay, what is the temperature now? What is the temperature at this point? Okay. And here, length is the thermometric property. So length here is the, or length in the column is the thermometric property. Thermometric property. And we can also say that this length is directly proportional to change in temperature, and that's how we measure the temperature. Now we have other device to measure temperature, which is called as thermocouples. So thermocouples are also used to measure temperature and how it works. So we can understand again by defining it. So thermocouples are like joints of two dissimilar metals. So when two dissimilar metals are joined, an electromotive force, EMF, or voltage that is primarily a function of temperature, will exist in a circuit. And we can measure that voltage difference, and we can say that, okay, so suppose if I draw this, suppose this is metal 1, then this is metal 2, and suppose this is hot, this is cold, then you can actually measure voltage difference between them, and this will give you, so this voltage is directly proportional to the temperature, and if you can read this voltage, you can scale it to temperature. And various wires which are, so these two metals have certain combinations. For example, this can be copper plus strontium, which is Ly of copper and nickel. So by these things we can measure temperature, and now we have different scales of temperature. So it is just to know these terms so that when we go further in the lectures, we know that, okay, if we are talking about Rankine scale, what is the temperature? If we are talking about Celsius, what is the temperature? So there are various temperature scales which are also defined, and I will mention here a few of them. So there is one Rankine scale where the temperature in Rankine is equal to 1.8 times the temperature in Kelvin. And you see that Rankine is written with a degree sign, but Kelvin is not written with a degree sign. Again, temperature in degrees Celsius is equal to temperature in Kelvin minus this number, 273.15. And we will see what is this number. So this number is nothing but the ice point of water. Okay. Then there is another scale, which is degree Fahrenheit. Temperature in degree Fahrenheit is equal to 1.8 times temperature in degree Celsius plus this number, 32. And having known all these three properties, which are a specific volume, so we just saw it is like 1 over this, 1 over density, a specific volume, pressure, and temperature. Now we are at a stage to define a more important concept, which is called a state postulate. And I'm going a bit fast because we can do some revision classes later. So right now I'm just pulling out the concepts which are very important to understand thermodynamics, and then later we will see how to revise these concepts. So a state postulate is also a very important concept here, and the state postulate, we can understand that it basically comes from the properties definition. So, and we understand from our lecture 1 that a state can be defined fixing the properties. So state postulate says that the state of a system, a state of a simple compressible system, and simple compressible system also has one definition. So right now we are just writing it, and then later we will see what a simple compressible system means. So the state of a simple compressible system is completely specified by two independent intensive properties. So this is a kind of a statement which is known as a state postulate. And one thing I want you to note here is why it is specified by only two independent properties, because for a system, and later we will see that energy transfer was actually responsible for change in pressure or temperature, and energy transfer in thermodynamics can happen only like by two means. One is heat and another is work, and that's why we only need two independent intensive properties, and we will see it in coming lectures. I will remind you again that why we can only change energy of the system by either heat or work. Now we need to define the simple compressible system. So simple compressible system means, so if a system is a simple compressible system, means that we are ignoring or we are neglecting effects. For example, so a simple compressible system neglect, what do we need to neglect? So neglect electrical effects, neglect magnetic effects. You can also neglect gravitational effects. Then we need to neglect surface tension based effects. So if these effects are neglected, then we can call the system as simple compressible system. And with this, we have come to an end of our first part of the thermodynamics, which is mostly written in all the thermodynamic book as chapter 1, which is introduction in some books or basic concepts in some books. So we have come to an end of that chapter, which is introduction to thermodynamics and then basic concepts. And then in lecture 3, we are going to start the concept of energy, and we will see how the energy, like what I talked about, like heat and work. So we will see that energy has also a very important role to play in thermodynamics. And then we will define first law of thermodynamics. And we will appreciate that first law of thermodynamics is nothing but law of conservation of energy. So with that, I will see you in the next lecture, which will be lecture 3, and that will be uploaded very soon. And thank you once again for paying your attention. Thanks a lot.